Hi all, thanks to the organizers for putting together WOPM 2024 and for keeping this series of workshops going. My name is Kostas, I'm from ICFO, and I will describe our recent progress on mass-producible OPMs that we develop at ICFO, mostly for MEG, but also for other applications, in collaboration with our partners in Europe, Megin, VTT, Vigo Photonics, Aalto University, and CSEM. The work I will be describing today was performed during the OPM MEG project, which is funded by the European Innovation Council. And here I list the different partners in this project. It's a continuation of the Maximal project. And we at ICFO, we are mostly responsible for the characterization and the magnetometry and the physics of the sensor. And I have highlighted with blue also these other tasks because the talk I will be describing today is associated with these tasks and also, of course, with the corresponding partners. And it's going to be a continuation or an update on previous WOPM talks from people of our consortium. Okay, the talk will be covering these two publications. I will mostly focus on this first one regarding the fabrication and design of functionalized vapor cells for spectroscopy and magnetometry. It's already available on arXiv, and feel free to scan this QR code for more details about this publication. To give a bit motivation, I will be talking about the OPMs for MEG, and conventional squid-based MEG systems are typically very bulky. They require cryogenic cooling, and they offer low mobility to the patient. Whereas on the contrary, OPM sensors, when operated in an array and integrated in helmets like we see in these pictures, offer high flexibility, better proximity to the scalp, and also comparable sensitivity to that of squid sensors, or even better in some cases. Nowadays, wearable MEG systems, like the one we see here in this picture, consist of 100 to 200 sensors, and one can see that mass production is really an important challenge in such systems because to put some numbers down, we can imagine that one would like to produce hundreds of such helmets. Each helmet has hundreds of sensors. Therefore, we are talking about 10,000 of sensors. And mass production is really a big challenge because we need reliable fabrication of miniature sensors and automated and rapid assembly at the wafer scale, high integration with robust technology, low cost, etc. But also, there are also engineering challenges like low crosstalk between different sensors. Each sensor has to have high sensitivity. We need to operate at zero field to compensate for to increase our dynamic range, but also thermal management is a big issue because each sensor should operate at temperatures higher than 150 degrees. Where, for example, we can see here this DIL-14 clock developed during the Maximal project by components like a cell, surrounded coils, photodetector, laser unit, and some optics, all closely packed in such sensors. And here on the right, we can see a prototype sensor we developed during the Maximal project. And I would like to highlight that in this talk, I will mostly focus on the miniaturization of vapor cells and clocks, the miniaturization that happens only in this green part of the sensor, and I will not talk about laser or optics. The working principle of this magnetometer is very simple. There is a circularly polarized laser beam that optically pumps the vapor. And when the atoms are pumped, then the medium becomes transparent, and we see all the transmission, all the light passing through, and the intensity follows this Beer-Lambert law. There is exponential decay depending on the optical depth of the medium, but also on the spin. And in the presence of the transverse magnetic field, the spin starts to misalign and therefore starts to precess, and the transmission drops. And if we want to describe this schematically, we see the optical transmission as a function of the magnitude of the transverse magnetic field, and we have at zero field a transparency window of few tenths of nanotesla, which drops roughly as a Lorentzian at higher magnetic fields. Now, to operate this system, here I have a real-time implementation of this zero field resonance effect in the lab, where we can see that as we sweep the magnetic field around zero, we see this blinking there, transmitted light becomes maximum at zero field. Now, to operate this system as a magnetometer, we modulate the transverse magnetic field, and we demodulate the transmitted light to get the magnetometer signal. Now, we use these sensors, and we test them, the vapor cells, the coils, in this testbed setup at ICFO. We sandwich the vapor cell between these two biplanar coils, these green PCBs that I'm going to talk in a minute about, and everything is in this casing, is placed in this casing with an thin layer of aerogel for insulation. And then this sensor module is placed in the magnetic shield. We use 3 layers of new metal and a layer of ferrite. The residual field in the shield is about tenths of nanotesla, but then we use the SIM coils to reduce it even further to the order of 1 nanotesla. And then we use a high power Vexel laser of 1 milliwatt and some optics to polarize the beam. Then we use a commercial lock-in amplifier to modulate the transverse magnetic field, and we demodulate the optical transmission. And the output of the lock-in goes to a data acquisition system, and we also use function generators to produce test signals to test our sensors. A bit about the coils. These coils are designed by Megan, our partners Megan. These are field color loops, which are designed using the B-field software, software designed by Megan. And these are printed in this FR4 fiberglass PCB, 3D printed. It's a 4-layer PCB, and these coils can produce magnetic fields along X, Y, Z directions. And these current loops are developed and designed having in mind some design constraints. Some of them are related to the magnetic field, but some others are geometric constraints. For example, we want as high field homogeneity as possible at the place where the vapor cell is placed at the sensor volume, but also we need minimal stray field to avoid crosstalk between different sensors. But also there are geometric constraints, like this hole, for example, should be as close as possible to the edge of the PCB such that the standoff distrust from the scalp is minimized. We have performed simulations, but also measurements, both of the field homogeneity and the stray field. And we find that the stray field along all these all X, Y, Z directions is below 1% at a distance of 20 millimeters away from the sensor. Now we move on to the vapor cell. There are certain challenges that we face while miniaturizing the vapor cell. For example, as we miniaturize, we have shorter path to the walls. This means that there are more atom wall encounters and there is more wall relaxation. And to compensate for that, we need a higher buffer gas pressure. But also, miniaturizing means that we have shorter optical path length for the laser beam. And the fact that we have also high buffer gas pressure in the cell broadens our optical lines, and these together lead to smaller optical depth, meaning, let's say, lower magnetic signal. And to compensate for that, we need to increase the cell temperature to increase the optical depth, but this has more challenges. We need more insulation, larger standoff distance. This leads to larger standoff distance, and of course, worsens our signal. To address these issues, we use thermal functionalization. We use integrated platinum heaters on the vapor cell, metal functionalization. In this way, we can heat locally the atoms with lower power, but this brings on the table new challenges, like, for example, what is the heater magnetic noise produced by the heaters and the thermal magnetic noise from these current traces. And to quantify these noises, we refer to this table by NIST, published in 2010, where they describe the limits on magnetic sensitivity due to thermal magnetic noise in nearby materials. And there are certain concerns regarding the resistivity of the silicon body, also the condensation of rubidium in the vapor cell on the glass, and some concerns regarding the heater connections and the heater traces. Keeping those things in mind, we decided to go with this dual vapor cell, dual chamber design, where it's a high Z silicon body. Each chamber has a dimension of 4 by 4 by 1.5 millimeters, and we have microstructured thin film platinum traces deposited on the glass, which work both as heaters and as temperature detectors. Sorry. The reservoir chamber is where the rubidium source is placed, and the sensing chamber is where we perform magnetometry and the laser beam is passing through. And there are micro channels of a diameter of less than 1 micrometer where they connect these two chambers. And there are these traces where they are wire bonded on a hosting PCB. The fabrication sequence of this cell, these cells were designed and fabricated at CSEM. Briefly, what they do, they have the silicon wafer. They use deep reactive ion etching to create these voids. Then they anodically bond the bottom glass. They coat with aluminum oxide all the internal surfaces of the cell. Then they micro-dispense rubidium azide in the cell. The top glass is anodically bonded, and then the wafer is etched. In our case, we have an extra step in this sequence where these heater traces are lithographically deposited in the glass. After the vapor cells are filled, we use UV radiation in the whole wafer, and we radiate for months such that the rubidium azide is decomposed into rubidium-87 and nitrogen buffer gas. And in this case, we can achieve very high buffer gas pressures. Since after the cells are fabricated, they look like this. There is a lot of condensated rubidium on the glass, both of the sense chamber and the reservoir chamber. And actually, this rubidium azide decomposition process produces a lot of rubidium. And we use a heating process where we heat continuously the vapor cell with 1 watt of power at 100 kilohertz AC. And after 3 hours, we see that the condensation from the sense chamber has all moved to the reservoir chamber. And at this point, we have a temperature gradient between the two chambers, which is about 40 degrees Celsius. To characterize and calibrate our temperature sensors, we use this formula, which relates the resistance of the sensor to the temperature. There is a characteristic resistance, excuse me, and at room temperature, and this alpha here is the temperature coefficient of platinum. And we can see that this characteristic resistance depends on the length and the area of these current traces, where we cannot really know very well in our case. So we decided to measure and calibrate our sensors. So we immersed the whole vapor cell in an oil bath together with a K-type thermocouple, and we heated up the oil bath using a heat plate at 140 degrees, and then we let the oil cool towards the room temperature. And while doing so, we are continuously monitoring both the resistance of the RTDs and the temperature of the bath. And then using this formula, we fit the data, and we can find the R0 and A. And A was very close to the values we can find in literature regarding the temperature coefficient of platinum, and therefore we believe that this calibration is valid. Since we have calibrated our temperature sensors, we perform some characterizations on the cells. We perform absorption spectroscopy by scanning the wavelength of our laser beam using linearly polarized light at different temperatures, and we fit the absorption spectra using this Beer-Lambert law with a Lorentzian broadened absorption cross-section. And from its extracted number density from this fit, we associate two different temperatures, one coming from the reservoir RTD and the other from the sense chamber RTD. And this black line is the Killian formula, and we find good agreement with this theory. And also from these fits, we can extract the pressure broadening, which was about 40 gigahertz, and the pressure shift was about 18 gigahertz, and this lead to a number density of 2.6 amagat of nitrogen, or 3 bars at room temperature, roughly. Finally, we use these cells to perform magnetometry. There are certain parameters that affect the magnetic sensitivity. Some of them are related to the fabrication of the vapor cell, like the buffer gas and the path length. Some others need to be externally optimized, like the cell temperature or the modulation strength and modulation frequency. And to optimize first the temperature, we look at the zero field resonance as we scan the transverse magnetic field and at different temperatures. And we look at the sharpness, which is the height of the peak over the line width, and we try to see where the sharpness is maximized. And in our case, it was around 200 degrees. And after maximizing the temperature, we optimize the rest of the parameters of the magnetometer. We modulate at 790 Hertz with 35 nanotesla amplitude, and we obtain a sensitivity of 18 femtotesla per square root Hertz. The frequency range from 0 to 100 Hertz, which is relevant for MEG. And to quantify the sensitivity, we use this formula here. So finally, we compare this sensitivity that we obtained with the sensitivity we obtained in this previous publication, where we were using same dual chamber vapor cell, but without the thermal functionalization, without the metallization on the glass. We were heating using a ceramic oven here up to 150 C, and we obtained a sensitivity of 20 femtotesla. Therefore, we conclude from these two measurements that the thermal functionalization doesn't really add some thermal magnetic noise to our system. With that, I would like to thank the Atomic Quantum Optics group at ICFO, especially Morgan, Michael, Harini, and Rachel, but also our collaborators, Megan, CSEM, Aalto University, DIGO, and VTT. And I would like to mention that we have open PhD and postdoc positions